Hello, everyone, and welcome back to the Brainstorm Podcast. On this podcast, I talk to thought leaders in the field of neurotechnology. Today, I'm excited to be joined by Dr. Amy Rochford. Dr. Rochford is a pioneer of biohybrid neural interfaces. Biohybrid interfaces combine human stem cells with traditional electrical neural interfaces to allow for better integration into tissue, which has many benefits, as we'll soon get into. Amy received a Bachelor's of Science in Biomedical Science from Cardiff University in 2015, graduating with honors, her Master's in Nanotechnology and Regenerative Medicine from University College London, and completed her PhD in Engineering, Bioelectronics, and Clinical Neuroscience from University of Cambridge in 2021. She now works full-time at Science Corporation as a member of the technical team. Amy, thank you for joining me today on the Brainstorm Podcast.
Thank you for having me.
All right, so I want to get a more detailed view of your background. So can you tell us what your background is and how you got interested in neurotechnology and then specifically these biohybrid interfaces?
Yeah, of course. So at its simplest, I'm a biologist by training. So I did my PhD in electronics and I love being at the interface between two fields. So as you mentioned, my undergraduate is in biomedical sciences from Cardiff, and then I have a master's from University College London in nanotechnology and regenerative medicine. This is where I studied how stem cells grow on various topographies and materials. Shout out to Gavin Gell, who run this program. It was absolutely fantastic. He's kindly invited me to go back and guest lecture about some of my work. So I did my PhD at the University of Cambridge under George Maliaris. So he's the Prince Philip Professor of Technology. So he's widely regarded as the father of flexible electronics using modern material science. So things like P.PSS, Paralleling C. He was a wonderful supervisor, absolutely great mentor. I was between the electronics department and the neuroscience departments, which was great. I was fortunate to have opportunities to collaborate with, various academics. I admire being, between neuroscience, stem cell biology, chemistry. I came out of my PhD with a couple of papers. So my core research paper showed functional neurological restoration of a biohybrid neural interface in a rat peripheral nerve injury model. After this, I was awarded an EPSRC Doctoral Fellowship Prize for my work as the top PhD student in physical sciences at the University of Cambridge. But I ultimately turned down that fellowship to go into industry because I really want to be working on the best technology and getting that into patients. So I'm sat here in San Francisco Bay Area now, and I've been here for about a year. So going back to your question of, what got me into neurotech, I think the thing that drove me to neurotech is hugely my passion behind like treatments, devices, or any technology that can support brain or nervous system injuries. Because it affects, so many people's lives, this type of thing. And my sister Zara, I'm the oldest of 6 sisters, by the way, which is really fun. Wow. She lives with cerebral palsy. So this kind of drove my inquisitive mind to ask, can we treat her condition? And drove my original interest in the field. So it wasn't really until my PhD that I had my first practical hands-on experience with neurotech. I was bringing my experience in cells and biology to a lab that had a huge expertise in electronics itself, which was really exciting. So I got to experiment with the most cutting edge fabrication techniques. And I had to learn fabrication from scratch. I remember feeling incredibly overwhelmed by having to learn fabrication from scratch as a biologist. Huge imposter syndrome. I actually went and bought Electronics for Dummies book in the first month of my PhD, which is kind of funny now. So at the time, I was the first biologist in the group, or George's group in Cambridge. So I had to build the entire lab from scratch. This was, incubators, protocols, microscopes, the lot. And I remember telling my now husband the shock that I had of equipment sales reps would contact me all the time. They would show up at the building in engineering and just pretend they had meetings with me because they heard that this PhD student was trying to build a lab. So that was huge credit to George. He had a great lab coming from France. He brought his postdocs. So at the time he was moving from France to Cambridge to build the bioelectronics lab. So I think when I started, George had 8 people in the group. I was one of the first PhD students, which was a really awesome opportunity. And when I left, I think there was over 50 people. So his group was, really great. And thinking back, it feels quite, startup-y now. I think we were building things from scratch, trying new things, big ideas, as well as needing to like deliver papers and results at the same time.
That's amazing. And I love too how you gave us that progression of starting with a little bit of overwhelm, being like, okay, this is a lot of complexity, but I have passion for this. I want to work in this direction. And I know a lot of people start in that area. And so it's really cool to hear your story of how you started from, okay, what do I do? What's the next step, to doing some really impressive and pioneering research. So I want to get into some of that research. There are two papers that I'm aware of that you were the first author on recently. So one of them is Biohybrid, Biohybrid Neural Interfaces. And so I think that was your PhD work. That was a review article, right?
Yeah, correct. Yeah.
And then the other one, which you mentioned briefly, functional neurological restoration of amputated peripheral nerve using biohybrid regenerative bioelectronics. And I do want to say, before I ask you some questions, that these were really, really well written. It was not too complex, but in terms of not too complex for difficulty of reading, but it covered a wide scale of this field. So I really appreciated reading this, especially because I knew very little about biohybrid interfaces before getting into this. But okay, so we've said biohybrid interfaces many, many times. For people like me that before reading your papers wasn't too sure of what this means, can you tell us what is a biohybrid interface?
Yeah, of course. So the biohybrid neural interface is kind of a technological system that integrates both biological and artificial components to essentially establish a communication pathway between the nervous system and external devices. So if we're talking about it in its perfect form, it kind of facilitates bidirectional communication. So that comprises of like recording and stimulation capabilities. So the biohybrid element of the actual neural interface looks to overcome some of the challenges that non-bio-enabled devices potentially provide, and can overcome some of the benefits of cell therapies. So they offer several advantages over purely artificial neural interfaces by utilizing living cells and also living tissue. So they can provide better compatibility and integration with biological systems, which can then improve, long-term stability, reduce immune responses, and tissue rejection. So this also allows, for enhanced signal quality and specificity, and biological components can, process and interpret neural signals more effectively. So the biological component being either the cells or the tissue. And as you mentioned, the review that I wrote in 2019. So that was, when bio meets technology. It's kind of open access. And I think this really helped me, writing and researching for this helped me understand like the field as a whole. I think it's one of the most cited reviews on this topic at the moment. And as you mentioned, I've been told it is a great prime for people like interested in the space. So this, it comprises of like, biohybrid targeting central nervous system, peripheral nervous system, and also special sensors.
Yeah, it was really great to see that you gave quite a bit of history as well. And so you talk about some central nervous biohybrid interfaces, and then some central nervous system biohybrid interfaces, and then some peripheral nervous system interfaces as well, which I know is the research that you focused on. But yeah, it was, again, a great primer for me to see all of the depth of this field and everything that's there. And it's interesting as well because I'm familiar with optogenetics, and so this was like thinking of it within this scheme. So I know you talked about that a little bit, but yes, it was all very interesting. So can you tell us a little bit about specifically the devices that you've worked on, and how do you make this device? So you're talking about, okay, we have electrical components, which is more traditional neural interface, and then we're bringing in these stem cells. So how does that process work? What is implantation like, and how do you get data out of it?
Yeah, of course. So yeah, as you mentioned, like making the electronics element of the device, you can use like lots of different techniques. So you can make thin film electrodes, micro LEDs, thin film transistors. For my PhD, as you mentioned, we developed this new category of neural interfaces comprising of these induced pluripotent stem cell-derived myocytes. These are human muscle cells. So these were used as a target for the peripheral nerve input that was grafted onto this flexible array that I described. So I used thin film bioelectronic devices. These were P.PSS coated electrodes, and these were insulated in Parylene C. And these were techniques developed in George's group. And these created like beautifully flexible devices. And it was like the cling film, basically. And you guys call it cellophane here. It's a very flexible, static, essentially material. Different materials pose different challenges when it comes to the cell part of this. So the best example I can give is trying to stick Jello to cellophane. So if you're like in your kitchen and you're trying to put Jello on cellophane, it'll just slide off. And that's what like putting cells on bioelectronic devices is essentially like. So you have to play around with the materials and the surface properties to get these cells to stick, whether that's incorporating hydrogels, that type of thing to encase these cells on the device. All the material scientists that are listening will have their views on trade-offs of popular materials for invasive bioelectronic devices regarding their durability, their longevity in the body versus their biocompatibility. So the unique aspect of my research was embedding these devices with cells. And in the case of my recent paper, this is the peripheral nerve injury rat model. And I encased these with human iPSC-derived muscle. So the components of this, I made the devices in the clean room, how you normally make thin film bioelectronic devices. And then I took these out and I had to work out a way to adhere cells to them. And these had to be then prepared for surgery. So what that entailed was me making like a little contraption out of like cell culture plates and PDMS and keeping my devices somewhat secure during the cell culture process of this protocol. So I had my bioelectronic device connected up to a flex cable that was prepared that could be implanted in theory on its own, and that acted as the control group for my experiment. I seeded these stem cells on top of the device. I used certain protein coatings before to get these cells to adhere to this, what is a hydrophobic material initially. I grew stem cells on the top for about 8 to 10 days until they were in their mature muscle state. This is really important because you don't want to be necessarily implanting pure stem cells into the body. They could have the capability to differentiate into anything. So I made sure that they were somewhat differentiated so that this wasn't the case. When these muscles looked really nice and striated on my device, as I mentioned, between day 8 and 10, these were then ready to be implanted into my rat model. The rat model itself took quite some time in my PhD to develop because I had to develop a model where we could actually run things like histology after the experiment had been run to show that the cells had survived and incorporated in the body. So this was one of the biggest challenges, I think, interfacing like the device with the nerve and in the correct orientation. That meant that like I could access it. I could run acute electrophysiology. I could run a freely moving electrophysiology where the animal was awake and it was reaching for like treats that we were giving it. So that was really exciting, but also like quite difficult looking back now. So the importance of like growing these human muscle on the actual bioelectronic device itself, interfacing with the forearm, kind of had this hypothesis that if we could create a neuromuscular junction between a human grafted muscle and the damaged peripheral nerve in the host rat, this could, in theory, amplify the signal. And this is really important, as you know, when you're recording from bioelectronic devices. So that's just kind of a crash description of like what I worked on for my PhD. But I wanted to shout out to Mark Cotter. Sorry, my notifications are loud. I wanted to give a shout out to Mark Cotter and BitBio for the amazing cells that they supplied. So that's, collaboration with Mark. I learned how to grow iPSCs from scratch and differentiate them into different cell types. I also believe this was the first time that we'd actually put these cells in an animal model. So this was really interesting, like twofold in terms of bioelectronic devices and also these human cells surviving an animal model. And the company now has gone on to do great things, which is really exciting.
Fantastic. So you have your neural interface, you have these cells that you're growing in culture, and then you're putting that into the body. So these cells are acting as, I think in your paper, you described it as a bridge to help connect the tissue in the animal, in the rat model, to your neural interface. So does that help you? What advantages does that give you? Does that help with biocompatibility, longevity?
Yeah, exactly. So The best way I can think of describing it is saying that like I developed a plug into the nervous system. So in essence, you can say that I've created like a living interface that allows a connection between living nerves at one end and electrical components at the other. So for my recent paper, we showed long-term survival and functional integration of the Biohybrid device that carried these human iPSC-derived cells. So this was following like a 4-week implantation. So we showed that, by embedding these cells in the device, we could show that it survived and integrated in the animal that we were testing, which was great. And the really exciting part was that we showed that we could get improved integration of these devices, which then, as you mentioned, has a huge number of benefits in terms of, potential long-term stability and survival of this device in potentially a patient in the future. So by improving that tissue electronics interface with that intermediate cell layer, we demonstrated enhanced resolution and electrical recording in vivo as like a first step towards potentially restorative therapies in this bioelectronics regeneration field.
Is it difficult to get the cultured stem cells to connect in the right place, or like to connect in the right place in the tissue?
Yes, so that is a good question. So I think that's why the model that I developed was really important, because these cells are firstly cultured in vitro and they're used to living on that device for 8 to 10 days, and there was questions of whether they would survive. So that's why I incorporated different hydrogels into my optimization techniques. So getting these cells to survive on a device without any of their like cell culture media is quite difficult. So I tried various hydrogels that basically encased these cells onto the device during implantation, in the hope that like there would be extracellular matrix components in there that the cells recognize. So when they were interfaced with the nerve, that might help them integrate. Also, when I actually did some tests with these cells without hydrogels, and it's you find that they shear off during like surgical implantation. So these hydrogels can also additionally act like an intermediate layer and help survive of the cells. So I used a biodegradable hydrogel that in theory degenerated at the same rate that the nerve was integrating with the muscle. So it would protect them somewhat, but also break down as well in the body, which was pretty cool.
Definitely. So how long does it take to get stable signals from these interfaces once implanted?
This is a good question. So because I was focusing specifically on the peripheral nervous system and, as I mentioned, this neuromuscular junction, I wasn't expecting to see any improvement until after 21 days. We know that neuromuscular junctions take about that time to grow in vivo. So when I was testing this week by week and I was not necessarily seeing improvements, it's just like, oh, maybe this isn't going to work. And then after, 21 days, we was like, oh, maybe there's improvements. And then it just vastly improved, between the 21 to 30 day time point. I think initially the plan, I was just, oh, maybe I just do 21 days and see. And I'm glad I kept it going on longer, because then we just kept seeing vast improvements week by week. So that was great. But yeah, it takes a long time, obviously, because these, you're incorporating a biology perspective to the bioelectronic device. You can't necessarily speed up biology. So once it's in there, it is a waiting game to see whether you really are going to get that improved, signal to noise ratio and signal amplification.
Absolutely. So I know that there were lots of pieces of media that came out commenting on the findings in your papers, and a lot of them mentioned the potential use for prosthetics. So I'm curious, what do you hope this technology could be used for in clinical translation? So prosthetics, what else, and how could that be used?
Yeah, so broadly speaking, I think biohybrid interfaces represent, in my opinion, like the most exciting frontier in BCI research and development right now. Because like the core facet of the approach is described before as like improved integration of these interfaces. So this removes a number of critical issues that we face in like the invasive device field. So in theory, less foreign body reaction that's related to, fibrotic encapsulation. So this is where, you get that thick body of like collagenous tissue around a bioelectronic device. So this then affects like whether those signals from that device can reach the target tissue, that type of thing. So for interfaces, it's like trying to have a conversation through a wall. So like the holy grail of neural interfaces is kind of like this perfect integration with no information loss when recording or stimulating. So I hope that, Biohybrid will act as like a stepping stone towards that. So I like to use the analogy that like existing neural interfaces, like trying to listen to a conversation through a wall, where like the biohybrid neural interface is like having a stethoscope. So the wall is a lot thinner, you got less foreign body reaction. And I kind of hope that this research can deliver like a step change in like device, resolution. So once fully tested, although I just did the proof of concept in peripheral nervous system injuries, I think the biohybrid approach could be like a gold standard for, invasive device interfaces. So if we think of it as like a platform technology where we could like embed devices in cells to treat a number of nervous system conditions. So whether that's central nervous system, peripheral nervous system, or special sensors. So currently, electronic devices and implantable bioelectronic devices provide like symptom management strategies to progressive diseases. But I think with Biohybrid, we could have this paradigm to move towards like curative solutions by combining the latest technologies in tissue engineering and flexible electronics, specifically for Biohybrid.
That makes sense. And transitioning a little bit off of that as well, one company that I've seen aggressively pushing clinical translation of this technology is Science Corporation, which is where you're working now. So I know that they're working on the Science Eye and potentially some other technologies as well that take advantage of these biohybrid interfaces. So could you just tell us what is Science Corporation? Let's start there. And what do you do there?
Yeah, of course. So I can only speak about the announced projects that we have at Science, but I'll open by saying that we're recruiting across like multiple teams. We've brought together some like incredible people from biology, fabrication, electrical engineering, and more. So at Science, we develop advanced technologies with a goal to overcome, kind of or blur between medical devices and consumer electronics. So today we're focused on like debilitating conditions for which there's a serious unmet clinical need. So as these technologies mature, they hold the potential to profoundly reshape human condition. So we have a broad mandate to follow interesting science wherever it like might take us in pursuit of like new products. So in terms of the Science Eye, we take a program-based approach, and our lead project is program 1, which is like neuroengineering. So this, as you mentioned, is our retinal visual prosthesis or Science Eye. So as we like continue to make progress, we'll announce both further projects within this area, as well as like other unrelated programs. So with the Science Eye specifically, we're targeting diseases like retinitis pigmentosa, macular degeneration, where light-sensitive cells in the retina, so the photoreceptors, are lost. And the cells of the optic nerve, so the retinal ganglion cells, or RGCs, remain, and this still causes blindness or vision loss. So the idea that we have is that since the retinal ganglion cells, the output of the retina, we could stimulate them directly and restore visual input to the brain, even without replacing the photoreceptors. So essentially it's kind of like a combination approach. So we're working on an optogenetic gene therapy, as well as a high resolution film display. And there's a preprint of this paper online if like anyone wants to go and read more about this. But in terms of like the specific device that we're working on, we describe in our paper that we've got a novel optogenetic visual prosthesis, and we call this the Flex LED. And based on a combination of, thin film retinal display and optogenetic activation of these retinal ganglion cells I mentioned, the Flex LED implant is about 30 microns thin. It's flexible, it's wireless, it's got a micro LED display with about 8,000 pixels. Each of these has an emission area of about 66 micrometers squared. This display is fixed to the retinal surface. So the electronics package itself is slipped under the conjunctiva, and this form factor is kind of the same as a conventional glaucoma drainage implant. So we use this in a rabbit model of photoreceptor degeneration. So we had optical stimulation of the retina using this Flex LED that elicits activity in the visual cortex, which is pretty cool. And this technology is kind of readily scalable to hundreds and thousands of pixels. So we're providing like a route towards implantable optogenetic visual capabilities of generating vision by stimulating these RGCs at like a near cellular resolution. which I think is really cool.
Yeah, that is. I mean, it's such a huge step up from any of the research that I've seen to date, and I know that there are multiple sites that researchers will target when trying to make visual neuroprosthetics, but targeting the retinal ganglion cells. Just for anybody that's not familiar with the anatomy of the eye, those are actually on the surface of the retina, and the photoreceptor cells are kind of behind it, which is a little bit weird. It might not be what you think is intuitive, but it makes it a little bit easier, I guess, to access these. And so, are you taking signals from an external camera and feeding that in? Is that how you're getting the original image?
So at this stage, it's proof of concept. So we're
Okay.
shining light through these flex LEDs, which then activate the RGCs and send signals down the optic nerve. And we've got an ECOG device which picks up signals in the brain. So at this stage, it's just proof of concept. So we aren't showing any smart images or that type of thing yet. But yeah, all of this is described in our paper, which is pretty cool. We've got some really great experts working on this, so it's exciting.
Yeah, no, it's incredible though that you're talking about 8,000 pixel resolution and potentially even higher. Just the ability to stimulate on such a granular level is impressive in any target. So that is really cool. So what excites you about science's overall vision of what they want to do in this field?
So I think what drove me to come here from England is that we're going to be working on issues that are going to impact millions of lives. There's lots of people that are affected by nervous system injuries, and working at such a multidisciplinary team at Science with world leading experts, working on the problems that we're trying to solve is just so exciting. And I think that in the future, these are going to be incorporated most of our lives. So it really excites me that I'm working on translational products that could be in patients in a few years.
Yeah, it's really it's been really interesting to see Science's rise. So Max Hodak is the person who founded it. He was formerly at Neuralink. So when he decided to leave Neuralink and start Science, I know that we were getting a lot of questions about, ooh, what is this? And it's been kind of elusive until recently when they showed that they were working on the Science Eye. So that's been exciting. And I know another initiative that Science has been working on is the Foundry. Can you tell us a little bit about what the Foundry is?
Yeah, no, of course. This is really exciting. So yeah, as you mentioned, we recently launched the Science Foundry. So since its sophistication of products, we can make depends on the tools that we have essentially and how quickly we can iterate on designs, etc. So at Science, we've invested heavily in our fabrication capabilities. So the Foundry means that we can build on some advanced fabrication infrastructure that powers our own research and development in-house at Science. So our facility is actually based in North Carolina, which we acquired from MEMSCAP last year. So it's currently ISO 9001-2015 certified. So we plan to configure this to support FDA GMP. This is good manufacturing practice production. So beyond medical devices that we're working on, we look forward to Science's emergent wafer service capabilities. So having an impact on advanced applications in aerospace, defense, quantum computing, optical telecommunications, among others. So the team's done an absolutely incredible job of building out documentation for the Foundry. So if you're interested or anyone that you know is interested in our capabilities or actively looking to reduce, micro electrical mechanical systems, please visit our website or reach out to Kara Zapatini, who is working on this.
So is this something that could be open to contract work for researchers or potentially a startup to get access to some of that technology?
Yeah, exactly. That's exactly what we're hoping for. So it's, as well as advancing our research and development, we're very aware that lots of other people are wanting to, make such devices, and there potentially is a bottleneck at, the speed at which these are made and how they're made. So offering this capability, can help other people in the field advance their developments, whether that's, as I mentioned, in science as well.
Yeah, I was very excited to see that when Science launched the Foundry, because it is so difficult and increasingly more difficult as the electronics are getting smaller and smaller to actually make these neurotechnologies. So it seems like a great way for researchers or other startups to be able to make the devices that they're trying to design without having to get all of this really expensive equipment or design new equipment to make these things. So that is something that I was really, really happy to see that Science was working on. Okay, so I want to ask a question here about for people that are just getting interested in the field. So maybe a high schooler or someone who's an undergrad that thinks that what Science is working on is really cool, what you worked on and your PhD research is really cool. What advice do you have for them for where to start and what they should do to start doing this type of work?
This is a great question. So I think that the neurotech industry is one of the friendliest multidisciplinary ecosystems that I've actually come across. So my suggestion is don't be a stranger. Send out that message or email to someone that you want to have a coffee with. You never know what it might, learn or turn into. I love doing this personally myself, like speaking to other people in the field. Generally, what's the worst that could happen? So if you're interested in an area, definitely go and learn about it. And if you're passionate about something, pursue it. So I know that like when I was doing my PhD, we had, high school kids that would like email in and ask if they do internships. We had like undergraduates and, George's ethos, he was so great. He was also like, you always want to give back. So if there's like a lab group that you're interested in that you just send an email, because it tends to be like we all want to help each other out and like get into that space. And also Science offers internships as well. So if people are, interested in coming doing internships, that's an opportunity too. And just to reiterate that most people are, really friendly and, we want more smart people working in this space. So yeah, don't let anything hold you back.
Yeah, I echo everything that you said about this industry being inclusive and welcoming of new people coming in. It's a growing industry, but it's still very small right now. And so there's a lot of willingness to help out each other. And yes, I think that a lot of times you won't find a job in a traditional way of like, oh, let me go find my, neuroengineering job posted on LinkedIn. So yeah, it's the best thing to do is just reach out, get in touch with people. And yeah, it's good to hear that advice coming from you as well. So for my last question here, what is your hope for the future of neurotechnology, how it could be used, how it shouldn't be used? And let's go maybe 15, 20 years out.
Oh, good question. So big picture ethics, fundamentally, I care about helping patients and my hope that the best tech can lead to better treatments. So it feels like neurotech, like in this space, makes such amazing, great strides year on year. And I'm really excited about that. So I love seeing like more smart people come and work in this space. We've got more funding for labs, companies. And I remember actually having a discussion way back in 2019 at the iHuman report at the Royal Society. So this is in England, and they were developing a report to talk about ethics, the future of neural interfaces, and that we need to catch up with from an ethics perspective, which was really interesting. An important point that was made around this was patient advocacy. So I'm really glad that since there's been some vocal patients and advocates in this space, like Ian Burkhart, it's really inspirational. And this week, we saw, a lot of patient-focused research, Cortine's lab from EPFL, they posted their research this week on implantable devices actually helping patients walk, which is so cool. And I think in the future, and also we're touching on this now in terms of bioelectronic implants and neural interfaces, I think, if we're talking, you said 20 years time, it'd be great to have patients that have BCIs, that have intuitive control. So whether that's, patients that have got spinal cord injuries or any of the other conditions that I've mentioned, is that having intuitive control rather than having to control whether they want to move their prosthetic arm. It's actually just them thinking, I want to reach for my cup of tea and feel that it's warm, and you get bi-directional feedback and it's intuitive. They don't have to think I want to reach, they can just grab it kind of thing. So I have no doubt that the field is going to advance hugely with all of this awesome stuff that's going on. And I'm super excited for, to see what's going to come out of, the BCI space.
It is a really exciting time for sure. There is new research, there are new companies, new products popping up all the time. And yeah, it's a wonderful time to get in the space and to be in the space. So if people are interested in following you, following your work, and Science's work, where can they find you?
So yeah, that's a good question. Please reach out to me on like Twitter, LinkedIn, or email me. I think this is all you can access this all from my LinkedIn. Happy to chat to anyone that wants to get into this space. I'm super passionate about it, and I've been fortunate enough to have some great mentors along the way that have given me advice. So I would love to, anyone that's wanting to get into this space, happy to chat about that.
Fantastic. And I will make sure to put some links in the show notes to anything that you want to show, some of those papers, to Science, to your social medias. So you can find that in the description. Amy, thank you so much again for coming on Brainstream. This has been a wonderful conversation.
Thank you so much for having me.